next session. So this is the session on static analysis and abstract interpretation. And our first talk will be given by Vincenzo Arceri. And the title is Relational String Abstract Domains. Please go ahead, Vincenzo.
Okay, thank you. Can you hear me? Can you see the screen, right?
Yes, everything is fine.
Okay, perfect. So, hi everybody, I'm Vincenzo Arceri from University of Parma, and I'm going to present our paper, Relational String Abstract Domains, that is joint work with Martina Olliaro, Agostino Cortesi, and Pietro Ferrara from University of Ca' Foscari of Venice. So the motivation behind our works comes from the fact that strings play a crucial role in any programming languages. In any programming language, such as they can be used to dynamically inspecting objects or turning text into executable code, such as eval in JavaScript or Python, and also for handling data interchange formats such as XML and JSON. So if we talk about static analysis, in the last years, the static analysis community, also via abstract interpretation, has spent a great effort in proposing a novel abstraction, both general purpose abstraction and language-specific abstraction. So just to cite a few abstractions, we can have prefix, suffix, char inclusion, string domains. We can have also final state automata abstraction for analyzing strings, and also we have plenty of language-specific string analysis targeting a specific language, such as mstring for C programs, or string domains integrated into static analyzers. Just an example, like the string domain integrated into TAJS for JavaScript. But if we make a comparison between integers and strings abstractions, if we talk about integers, we have plenty of relational domains, meaning that the domains are able to track the relation between the variables appearing in a program, while if we talk about strings abstraction, actually most of the domains proposed to analyzing strings are non-relational, meaning that they are just able to track the abstract value on a single variable without inspecting the relations between the variables appearing in a program. So let's consider this simple example that basically takes as input three strings that are statically unknown, and the function manipulates them in order to compute a result. But if we analyze the function with non-relational domains, actually non-information can be computed about the returned value, because the parameters are statically unknown. But what we would like to infer, to retrieve, are like relations between the parameters and the return value. For example, it could be interesting to derive that when the variable name starts with PR1, the return value contains surely PR2, or dually, if the variable name starts with PR2, the return value contains PR1, or we could infer that the return value surely contains the substring of name from 4 to the end of the string. So the goal of our paper is to provide a constructive method to derive string relational abstract domains starting from a specific string order of interest. In particular, in the paper and also in this presentation, we will discuss these relations. Like, we would like to infer when a variable is a substring of y, where a variable, is a substring of another variable, or when the length of a variable is less than or equal to another variable, and so on. After that, we lift the framework that we have defined in order to handle not just relations between single variables, but relation between a general string expression with a variable. So, for example, we want to infer that the concatenation between y and z is surely a substring of x. And finally, we propose a combination between non-relational and relational string domains in order to improve the precision of non-relational string abstractions. So the framework is defined over an imperative toy language imp, and then the framework has been implemented for a prototype static analyzer for Go that I'm going to discuss at the end of the presentation. So, as I said before, the starting point of our general framework for deriving string relational abstract domains is an order over strings that can be a pre or partial order. And the first step is to lift the order in order to handle not string variables, but not strings values, but string variables. Okay. So what we aim to capture in our purpose is this kind of set of relations. So we want to capture that x is in relation with y, z is in relation with w, and so on. So from what we aim to capture, so the abstract domain is defined in this way. So as I said before, we aim to capture sets of this kind of relation plus a special element bottom. So this is the domain, and the bottom element is this special element bottom, while the top element is the empty set, and the partial order between elements of the abstract domain is defined in this way. So A1 is less or equal than A2 when E2 is contained into A1. So it is clear that we are aiming at capturing a definite information. What does it mean? It means that we want to track must relation, meaning that if something holds in the abstract world in our abstraction, then it surely holds also in the concrete one. So what we are missing now is to define other lattice related operators like list upper bound and greatest lower bound. So the list upper bound between A1 and A2, since we are keeping just definite information, is just the intersection between the two sets. And then we apply the transitive closure over the intersection in order to get implicit relations. So for example, if we have the list upper bound between these two sets, the only information that survives after the loop application is the relation that between x and y. Again, because we are aiming at capturing just definite information and not possible information. And in a similar way, we can define the greatest lower bound operator. So we have proved that the so far obtained domain is a complete lattice. So in order to fit the domain in a static analyzer based on abstract interpretation, we miss concretization and the abstraction function. And basically the concretization function given a set of relation, concretized that the set to the set of concrete memories where all the relations holds. Okay, all the relation in the input set holds, and the abstraction function can be defined in a dual way. And after that, we proved that the concrete domain and the abstract domain defined so far form a Galois connection via alpha and gamma functions. So this is the domain. So what we are missing now is to define the abstract semantics of our imp language. So we need to define the abstract semantics on statements that is given a set of string relations. The abstract semantics must return a new set of relation tracking the effects of the statement that is going to be analyzed. So, for example, if we consider this assignment, and let's analyze. Let's instantiate, the framework defined in the previous slides with the substring relation. So let's suppose to start with the abstract state reported here. The result of the analysis of the assignment is it tracks basically that Z and Y are surely substrings of X. Of course, in this case, the information about X is removed because we are going to update X, and so any information about X do not hold anymore. But if we consider this another example, X concatenated with Y assigned to X, and let's suppose to start from the same abstract state. In this case, the previous information about X survives because we are not completely updating, overriding X, but we are just appending new strings to X. So in this case, the information about X survives after the analysis of the assignment. So I will provide just the abstract semantics about assignment, and in a similar way, you can define the abstract semantics also of the other statements and expressions. So let's suppose to analyze an assignment of this form, and the abstract semantics first relies on an extraction function. So basically, the extraction function, given a string expression as input, returns the set of string variables that appears at the top level of the string expression S. In a nutshell, you can see any string expression as an ordered list of string expression put all together by the concatenation operation, and basically the extraction function retrieves the string variables that appear at the top level of this ordered list. So in this example, if we apply the extraction function on this expression, the result is Y, Z, and W. Okay, so the first phase of the abstract semantics of assignment needs to remove the relation, the string relations that surely do not hold anymore after the assignment. So if X appears at the top level of the assigned expression, we just remove any relation in this form. In all the other cases, instead, we remove any information concerning X, because if X does not appear at the top level of the string expression, okay, it means that X is completely overwritten, and any information about X do not hold anymore. So in this way, we remove the relations that do not own anymore. The second phase is to add instead the new relation that are introduced by the assignment. So basically, for any variable extracted by the extraction function, we add the relation, this type of relation. Okay, the new basically variables that are related with X. And finally, we apply the transitive closure on the obtained set of relations in order to add implicit relations in the output set. Okay, so this is the abstract semantics for assignment, but in a similar way, you can define the abstract semantics also of the other statements and the other expression and Boolean expressions. So we have instantiated the framework over three string orders: character inclusion, length inequality, and substrings. And the main difference between these three relations is that the first two relations are just preorders, while substring is a partial order. And the main difference is shown here. So let's suppose to have this set of relation, and let's suppose to wonder, okay, is x equal to y? In the first two cases, we cannot surely say that the two variables are equal, because the framework is based just on the instantiation, are based on just preorders, while if we have the framework has been instantiated with a partial order, we can surely say yes, because indeed is a partial order. Okay. So there is a limit about the framework defined so far, and for example, let's consider this simple example. In this case, of course, we are able to infer that if we suppose to instantiate the framework with the substring relation, we are able to infer that W and Y are surely substrings of X and Z, but we are not able to infer that Z is a substring of X. So the next step was to extend the framework that I have shown in the previous slides in order to track not just single variables, relation between single variables, but to track relations between general string expressions and single variables. So the extension is straightforward, and you can find all the details in the paper. But if just an example, if we consider again the example shown here, and we consider the substring relational abstract domain, we are able to infer that the substring of X are surely YW, and also the concatenation between W and Y, and also the variable Z. So we have implemented the framework in a prototype static analyzer for Go programs called GoLisa, that is built upon the static analysis library Lisa. And in particular, we have integrated the R subdomain, that is basically the relational domain, that tracks the expression, the string expression that are surely, definitely substring of each variable. So in our first evaluation, we have compared our sub over some test cases, and here I report just two example, and then we performed a precision evaluation with respect to some non-relational domain, asking both to verify both relational and non-relational assertion. And in particular, we have considered the prefix, suffix, char inclusion, bricks domains, but also advanced abstractions such as starsys that I'm going to discuss in a couple of slides. And in particular, we have shown that R sub is the only domain that is able to infer all the assertion, even if the assertion are relational and non-relational. So one problem about the abstraction we have defined is this one. So up to now, we have used the R sub domain as a standalone abstraction. And in particular, if we use this kind of domain in isolation as a standalone abstraction, we can easily use precision. So for example, if we consider this easy example, of course, we are able to infer that the strings A and B are substring of W, but we are not able to say that the value of W is definitely the string AB. So we are just able to track the relations between variables, but not the exact content of each variable. So we said, okay, we don't want to use this type of domains, in particular in this case R sub in isolation, but maybe they can be very useful if we equip non-relational abstractions, okay, with this type of domains. So the idea was to combine our subdomain that is our relational abstract domain with Tarsis, that is a non-relational string abstract domain. In particular, Tarsis is a finite state automata based domain, and in a nutshell, basically abstracts the possible values of a variable as the automata recognizing the possible string values of each variable. The main difference between with the standard finite state automata domain is that Tarsis works on an alphabet of strings and not just characters with a special symbol at top. That means any string. So basically, we have defined the reduced product between Tarsis and our sub, and we have shown that Tarsis can benefit in some cases from the information that is inferred by the R sub domain. So, if, for example, let's consider this program, and let's suppose to analyze the function write that basically counts the occurrences of the variable pt into text, supposing that text and pt are statically unknown. So if we analyze the function write that relies on the count function here, taken from the string package of Go. If we analyze the write function with Tarsis, the return result by Tarsis. Oh, I forgot to say a thing. Tarsis use the automata for analyzing strings and use intervals to analyze integer values. By the way, in this case, Tarsis returns that the number of occurrences of pt into text is the interval 0 plus infinity, and we have a little loss of precision because we know that pt is surely contained into text. So the 0 value is just noise for the abstraction. But if we consider Tarsis plus, that is the reduced product between Tarsis and our sub, we are able to keep the information that definitely the variable pt is a substring of text. So in this case, our sub can be useful to refine the semantics, the result produced by Tarsis. In particular, it just removes the point 0 in our abstraction in order to get a more precise result. In a similar way, our sub can help to refine the abstract semantics of Tarsis. So we performed a preliminary evaluation about performance between Tarsis and Tarsis Plus. In particular, we have crawled top 10 GitHub repositories manipulating strings, and we ran Tarsis and Tarsis Plus on them. We have computed the execution time of Tarsis and Tarsis Plus, and we computed the overhead added by our sub. And we showed that the overhead on average is no greater than the 3%, and in general, for each repository, the overhead is no greater than the 7%. So our sub is very performant from our preliminary evaluation, even because it provides an efficient implementation. So to conclude, we have defined a framework for generating new relational abstract domains, starting from a specific order over strings. In the paper, we have instantiated the framework with the substring relation, char inclusion relation, and the length inequality relation. But you can instantiate the framework with any pre or partial order, such as prefix, suffix, you choose. And after that, we have extended the framework in order to handle not just relations between single string variables, but between a general string expression and single string variables. And finally, we have provided a combination between Tarsis and our sub in order to improve the precision of Tarsis. So what now? Of course, we need to better investigate the combination, the reduced product between Tarsis And the R subdomain in particular, we want to refine the abstract semantics of other string operations, such as replace. We need to formally investigating also the precision increment gained by adding R sub to Tarsis, okay? And in particular, we have proved, if we talk about the framework we have defined, we have proved that the abstract semantics defined is sound, but we didn't inspect the completeness property. And finally, one interesting topic could be to study, okay, in the paper we have studied which variables or string expression are in relation with each variable, but it could be interesting to study which variables or string expression are not surely in relation with some string variable. And we think we can we can track this kind of information in our framework, but we leave it as a future work. So that's all. And if you want to get here more detail about the definition, the formalization of our framework, have a look to the paper. And if you want to play a bit with Golisa, I leave here the link to our GitHub repositories. So that's all. And if you have any question, I'm here.
Thank you very much, Vincenzo.
Thank you.
I might be taking questions because we could already read it out. Any questions from the audience? Let's get started. So you mentioned completeness here. Are you referring to the question whether the abstract semantics is the best abstraction, or do you really mean completeness in terms of precisely tracking these relationships?
I cannot hear you very well. Are you asking about completeness, I think?
So whether, when you talk about completeness, do you mean that the question whether your abstract semantics is the best abstraction with respect to the value operation?
Yeah, well, when I talk about completeness, I mean, okay, the abstract semantics we have defined is we didn't investigate it if the abstract semantics we have defined is the best one with respect to the domain we are using, basically. So what we need to inspect is if we have no loss of information applying the abstract semantics. We didn't expect this property, and we are going to, in future works, to inspecting. Actually, what we want to do is to automatically complete the domain in order to get a complete semantics, actually, with some abstract interpretation techniques like complete shell and complete course. But we didn't expect it for the moment.
Thank you. Any other questions? I have one more quick question. So when you talked about this extension of the domain to track relationship with arbitrary string expressions, it seems like this gives you a domain of infinite height. Or do you a priori pick the expressions that you track?
Okay, I didn't get. Well, are you asking about the finite height of the domain?
Yeah, I mean, once you add this extension to track arbitrary expressions, do you then get an infinite height domain?
Actually, let me come back to the framework. Actually, the general domain is, of course, parametric on the order, okay, we want to use, but actually it's parametric also on the program we want to analyze. Of course, if we instantiate the framework with any string expression, we could have termination problems, and we need also a widening to enforce termination and so on. So actually the domains, both let's say the plain domain and the extended domain, is parametric on the program So the variable of a program we suppose are finite, so also the domain is finite. And also for the extension, we derive is parametric on the program, and let me come back here. We basically get is parametric on the program, so we derive from the program all the string expression that may appear on it, in it. And from there, we derive the domain. So both the domains actually are finite, because it's parametric on the expression, the string expressions appearing in the program.
Okay, thank you very much.